Hi, this is Craig Garczynski, and welcome back to North Yorkshire, England, and this dramatic structure that's behind me called the Crimple Valley Viaduct. I'm standing here specifically today honoring one of the guys in our power quadrant of Ohm's Law, James Watt. And in 1769, James Watt patented the steam engine. He was from Scotland, and he was a mechanical engineer and inventor. In 1816, the steam engine locomotive was introduced, and then further down the line in 1848, there was about 6,000 miles of railway installed, commissioned throughout Great Britain, including this structure, the Crimple Valley Viaduct. George Ohm, who I'll talk about a little bit later, defined the relationship between voltage, resistance, and current. And this relationship he called, or we know it as Ohm's Law. If you're somebody that doesn't quite get math, and the math that's in Ohm's Law, and the math that you're going to see in AC theory, that's okay. You're in good company if you do. I get the math, and it excites me, but some people don't. And one of the people that didn't was the great Thomas Edison. He was brilliant in some ways, and something with the math just kind of threw him. In fact, he was quoted as saying, "At the time I did my experiments, I did not understand Ohm's Law. Moreover, I didn't want to understand it. It would keep me from experimenting." So there was something about the math that tripped him up. Let's talk about voltage and how we see it in the Ohm's Law wheel, and how it applies to the formulas that we're using, and just a little bit more expansion to give you relevance and meaning. So volts is a household term, as are some of the other terms in Ohm's Law. You don't have to be an electrician to hear that word and to use that word. When we look at it in Ohm's Law, in the wheel of Ohm's Law, Ohm's Law wheels can vary a little bit in how they give you the terminology and how they lay it out. So don't be too worried about that if you see an Ohm's Law wheel that looks a little bit different than another Ohm's Law wheel. They have the same concepts in it, they just might move around the values a little bit. Sometimes you're just going to see the quadrant that says the letter E, and that's it. And other times it'll say E with volts right next to it. So E stands for electromotive force, or EMF. Later in AC theory, we see with inductive reactance and capacitive reactance, we're going to see a counter electromotive force, or an opposing voltage, known as CEMF. If it was just called volts, it wouldn't really describe what it is. So I think it's correct to say E, even though it might be confusing to you, because that's not a term that you might use every day or use it in the field when you're talking about volts, using E. But electromotive force defines it a little bit better. If we just said volts, it's somebody's last name, like all these other pieces of Ohm's Law. Volts was named after Alessandro Volta, an Italian physicist born in 1745. Some of the other terms that are used along with voltage that are synonymous that you'll see or you've heard of are difference of potential. That's a big one. And then oftentimes difference of potential is reduced to simply being called potential. Common voltages that you see in the US are 120, 208, 277, 480. Those are common commercial three-phase voltages. The next one above that, and more of an industrial voltage, is 347, 600. And you might be thinking, I like to know why things are the way that they are. I'm somebody that questions things and gets to know the meaning and the source. And you might even look at that number and go, really? What is that? Why 208? Why 277 and why 347? Those seem like odd numbers to me. And the answer is that it's mathematically perfect. It has to do with triangles. As we continue on in AC theory, there's a whole bunch of triangles and the laws of triangles within. And typically with triangles, you're going to see squared and square roots. So the square root of 3 is one of the most common numbers that you're going to come across in your electrical career. Square root of 3, 1.732. And that number is, if you take on your calculator, square root of 3 times 120, it equals 208. Similarly, if you take 277 times the square root of 3, it's 480. So there's a relationship between those numbers. There's triangles behind the scenes in everything that you're doing, even if you know it or not. When you're bending conduit, the distance that you put between your two lines when you're bending an offset. If you're using 30-degree bends, you're using the laws of a 30, 60, 90 triangle. And you use a multiplier of 2 because 2 is the hypotenuse of a 30, 60, 90 triangle. And if you're bending an offset using 45-degree bends, you're using a 45, 45, 90 invisible triangle that's behind the scenes. And in a 45, 45, 90 triangle, you're using the square root of 2, which is 1.414. You're going to see the word nominal quite a bit in your apprenticeship and your career. So nominal voltage versus actual voltage. Nominal is what the system was designed to be, like 120 would be the nominal voltage, and then actual voltage might be what you're doing in the field with your meter, and you get 123 or 124.5. That's actual. So that's nominal versus actual. In a parallel circuit, voltage is consistent throughout the whole circuit. So if it's 120 volts at one point, it's going to be 120 volts at another point. When you're looking at an equation and trying to figure out which variable do I know, which one do I use next, where do I use my calculator, how do I figure out the other value, just remember in a parallel circuit, voltage is consistent throughout. And then in a series circuit, it adds. So if it's a purely resistive circuit, the total voltage, or ET, is going to be equal to E1 plus E2, and they add together to equal that total voltage. And that ties in with Kirchhoff's law. A guy named Gustav Kirchhoff, who was a German physicist, I think he was born in around 1824. He said in the Kirchhoff's voltage law, which is known as KVL, the total voltage around the loop is equal to the sum of the voltage drops within the same loop. Alternating current was chosen over direct current because it can be transformed. And so we have transformers, and transformers are inductors, and inductors have an inductance value in L. And they also have something that goes on inside, which I'll explain more next week, called inductive reactance, which is a type of resistance. It's not resistance, it's a type of resistance. It's an opposition to current flow. It's a CEMF, a counter electromotive force. And in an inductor and in a transformer, there are things that happen where things are out of phase with each other, they're opposing each other, and we create sides of a triangle. And when we create sides of a triangle, we have triangle formulas. And the greatest one that you're going to see in the next few weeks, if you haven't seen it already, is Pythagorean's theorem of a triangle, which says a squared plus b squared equals c squared. And c is our hypotenuse side of our triangle. So you're going to see that. You're going to see that voltage is still going to add in a series circuit, but it's going to add through a triangle formula. So you're going to see squared and square roots. So it's going to be quite a bit. But if you get the foundation of how voltage operates, then it's going to make that much more sense when you get into a complex formula. The next quadrant I'd like to talk about is amps. And depending on the Ohm's law wheel that you're looking at, it might just have a letter I there. Or it might say I and amps. Both. And amps, again, like volts, is a household term. A lot of the general population is familiar with the term amps. They might not know what it means, but at least it's something that's known or recognized. So we see the letter I, and you might look at that and go, when am I going to use the letter I? I don't use that in the field. This isn't practical. But I gives it a better explanation than what amps does, because amps is somebody's last name or a representation of that. I stands for intensity of current, and we usually just refer to it as current. In the amp quadrant, it's synonymous with load, draw. Those are terms that you'll see when somebody's asking a question about amps. They might say, what's the load of the circuit? And if you didn't know load was amps, you might think, well, what's the load of the circuit? Is that watts? What are we talking about? I don't quite get it. If it just said amps, it's not going to explain what it is. Like volts, it's somebody's last name. So amps comes from Andre Ampere, who was a French physicist born in 1775. And that name is, it sounds even more sophisticated if a French person is saying the name Andre Ampere.
André-Marie Ampère.
That's the term that you'll see in various textbooks. You'll see ampere, and then oftentimes it's just amps and abbreviated with the letter A. And a fun fact about Andre Ampere is that the Eiffel Tower, which was built for the World's Fair in Paris in the late 1800s, I think it was 1889, there's 72 names that are inscribed on the Eiffel Tower of engineers, inventors, physicists, and Andre Ampere is one of those 72 names that's inscribed on the Eiffel Tower. Similarly, but different, amps and volts in a series and parallel circuit. In a series circuit, current is consistent throughout the whole circuit. So that means that you can take your clamp-on ammeter at any point in a series circuit, and it's going to be the same number throughout the whole circuit. In a parallel circuit, it adds. So if it was a purely resistive circuit, and when I say purely resistive, that's just something with heating elements or incandescent lamps, even though when I say incandescent lamps at this point, since they've been phased out and replaced with CFLs and LEDs, saying an incandescent lamp is like talking about an 8-track player. But there are still incandescent lamps out there. They're just not being manufactured anymore. Outside of that, when we get into transformers that have inductance and inductive reactance, then we introduce new variables. And similarly to voltage, in a parallel circuit, the amps are going to add together, but they're going to add through a triangle formula, which has squared and square roots and Pythagorean's theorem, so you're going to see that throughout. And then if you are dealing with a series circuit, whether it is a purely resistive circuit or if it's a resistive inductive, RL, or a resistive capacitive, RC, or a resistive inductive capacitive, RLC circuit, if it's a series circuit and any of those, the current's going to be the same throughout the whole circuit. That's going to be helpful to you to remember that, because you're going to get into some complex formulas when you're looking at this at a circuit diagram and you've got 20 values that you need to fill out or even more, and you only have 2 to start with, and you might think, wow, where do I even begin? What's my first point to? I don't even know how to apply my calculator to these numbers. If it's a series circuit and one of the values is given to you of amps, go ahead and plug in that same amp value all throughout. The next quadrant is resistance and ohms. And this one's probably the easier one to remember versus I for intensity of current and E for electromotive force. R is resistance. And ohms is what we use in that quadrant, named after a German physicist born in 1789, George Ohm, and he spells his name without an E at the end of it, and I think the correct German pronunciation of that is Georg. So Georg Ohm, and if you speak German and I botched that name, I apologize, but I think it's something like that. And so resistance is, it's an opposition to current flow. Without resistance in a circuit, you have to have some resistance. Without resistance in a circuit, and if you have a closed loop that's energized and no resistance, you're going to have an excessive amount of current flow, overcurrent, and then we're going to, it's either going to be a short circuit, it's gonna trip a breaker, it's gonna have a breaker blow up, it's gonna blow a fuse. So we need resistance. We need that opposition to current flow in a circuit. Within the resistance family, I'm calling it, although you're not going to see that term in a Delmar book, I'm calling it the resistance family. We're going to see terms that are going to be used sort of interchangeably in that quadrant. And those terms are, because we're dealing with an inductor, because we're dealing with a transformer with AC theory, we are going to see XL, which is the inductance or inductive reactance, or the reaction within an inductor. That is an opposition to current flow. It's also an opposing voltage, which you'll read in your text, which is known as CEMF, or counter electromotive force. XL has a formula to it that you'll get into, and I'll expand more on later, but it's 2 pi FL, 2 times pi, 3.14, times the frequency F, times an inductive value L. It's answered in ohms. All of the values within the resistive family, the opposition to current flow, are all answered in ohms, although they all have slightly different characteristics to them. So if you're asked a question for XL, inductive reactance, you're going to answer that in ohms. And then similarly, when you've got a capacitor, you're going to have capacitive reactance, or the reaction that happens within a capacitor. It's known as XC, and that has a formula of 1 over 2 pi FC, which you'll see in your texts. And then we're going to see a value of Z. Or in the UK here, it's not Z, it's Z. And so Z stands for impedance. And impedance is known as the total opposition to current flow in an AC circuit. So when you're looking at your total values, when you're computing the circuit that's in front of you on the Delmar text, and you're plugging in your numbers and your values, and you got your calculator out, you're always going to see Z in the total column, where you see ET for total electromotive force. You're going to see IT for total intensity of current, and then right below that you're going to see Z, or Z, for impedance, the total opposition to current flow in an AC circuit. In a parallel circuit, it gets a little bit more complicated. And for some of you, you get this, and yep, you got it dialed in. And this is just this is a walk in the park. This is just a refresher for you. But for some of you, resistance in parallel is one of those that you might not be able to get your head around. It might not make as much sense to you. It's an inverse formula. And that formula looks like 1 over RT equals 1 over R2 plus, or 1 over R1 plus 1 over R2. It means that the more resistive values you have in parallel, the less the total resistance. They are inversely proportional to one another. There's a place that you'll see that term in your code book when we're talking about motors in Article 430. There's a table in Article 430, which is table 430.52. And in that table, and if you have your code book, just maybe flip open to that just so you can make that reference as I say that. And if you don't have your code book with you, don't worry about it. Just listen. It breaks out the types of fuses and circuit breakers in that table, and a certain percentage that's allowed for overcurrent protection. And you're going to see inverse time breaker as one of the breakers in that section. And inverse time breaker simply means that the more current flow that's on that breaker, the less time it takes to trip. The most complex formula that you're going to see probably in all of your 4 years is impedance in an RLC parallel circuit, because not only are you dealing with triangle formulas and a squared plus b squared equals c squared, Pythagorean's theorem, but you're also going to be dealing with this reciprocal, or this inverse value, 1 over RT equals 1 over R1. You're going to have that intertwined in there. So there's a lot going on in that formula. All right, the next quadrant is the power quadrant. And depending on your Ohm's law wheel that you're looking at, it might just say P, representing power. It might spell out watts, which is named after James Watt, who was a Scottish inventor and mechanical engineer, born in 1736. And if I took the train this way, I could be in Scotland in about 4 hours or so, somewhere in there. to James Watt's homeland. He did a lot of his studies in Glasgow, Scotland, and then later on in his career he moved down to Birmingham, England. Here you would say Birmingham. In the U.S. you would say Birmingham. I've been an electrician for a long time, over 30 years, and it's probably the most common one that I still use is watts equals amps times volts. I just used it the other day on something that I was doing on my job, and it comes up all the time. Not necessarily every day, but it's the most frequent one that'll come up. Out of the different values that you see in the Ohm's Law wheel, the two most common ones for me over the years have been watts equals amps times volts, and I equals E over R. Out of all those, the 12 that you see around the outside of your wheel, those are the two most common. And you might find the same thing, or you might find that you use there's a different one that you like using a little bit better or a little bit more frequent. Within power, we have what I would call the power family, or some texts will call it the power triangle. When you have just P, that is dealing only with a purely resistive portion of the circuit, and P is known as true power, or depending on who you're talking to, they might say real power. The power value within an inductor is VARS, stands for reactive power. It's VARS with then a small L next to it. So the reactive power of the inductor is how you would say that. And then within a capacitor, similarly, we have VARS and then a C next to it. So that's the reactive power within a capacitor. And then we have a total power value that is really common in the field that you know as VA. Transformers oftentimes are rated in VA, or KVA for thousands of volt amperes. And VA, the specific term for it, other than calling it volt amperes, it's called apparent power. So we have apparent power, VA, which is the total power value of the circuit. So when you're computing your electrical circuit values and you got your calculator out and you're plugging your numbers into all these areas, on the total part of your circuit you're going to have ET, IT, Z, and then you're going to have VA, which is apparent power or volt amperes. One of the values in power is something that's I think that it was James Watt's doing. He concluded that there was an equivalent, there was an electrical equivalent to what horses could do. And so there's a number that's given to that, and you'll see that in your text, but that number is 1 horsepower, or 1 HP, is equal to 746 watts. Now we take Ohm's law and we apply it to a couple of things that you're seeing in the field, and hopefully this makes that much more sense to you. If it doesn't already, hopefully with this lesson, maybe, pun intended, maybe some light bulbs will start going on, or continue to go on, and maybe even burn a little bit brighter. I have to quote this one from Thomas Edison. Earlier I said that he wasn't, math wasn't his thing, but he was a brilliant man. When he was creating the incandescent bulb that we know, and that has been phased out and replaced with the LED bulb, one of his most brilliant quotes was when he was asked about creating the light bulb, and he failed a number of times. In fact, that number was like over 700 times while he was trying to create that bulb that we know so well and we've used. Somebody asked him and said, "Hey, Mr. Edison, what does it feel like to have failed 700 times in creating the incandescent lamp?" And if that was me, I might have just kind of felt crushed by that, like, oh, yeah. Or maybe some of you would feel the same way. But he was so, as I said, tenacious. He was so fierce with his inventions that he said, "I haven't failed 700 times. I haven't even failed once. I have successfully proven that those 700 ways won't work. And when I eliminate all the ways that won't work, I'll find the way that will." On your job site, this term that's being used more and more, and that more of you are aware of every single day, is arc flash. And I know a situation where somebody, this happened to this a person, where they energized incoming feed to a large commercial building where they had paralleled 500s feeding that building, and 2 of them were crossed. And somebody flipped the switch on and it blew up. It was a bomb. It wasn't just a short circuit, it was an explosion and a bomb. I have 277-480 in that distribution gear, and I have 480 between line to line or phase to phase, 480 volts. And those two are crossed, or 2 of the parallel conductors are crossed, and I have a bolted fault which almost eliminates resistance, or makes it, another term that the code book likes to use, negligible resistance, which is not enough really to be considered. So let's say I have a 480 volt bolted fault and my resistance is 0.01 ohms. So on your calculator, I equals E over R. So on your calculator, if you do 480 volts divided by 0.01, the answer is 48,000 amps. That's why fuses and breakers have a rating on the side of them that's an AIC rating, an amp interrupting capacity rating. That's usually has a K in front of it for thousands. The minimum residential breaker is 10,000 amps of available fault current that it can handle and still do its job. I'll use a smaller number and give you relevance to Ohm's law. Let's say you get an electric shock. Say you come in contact with an energized circuit and you are, in order for current flow to happen, you need a closed loop and you need voltage. And so let's say there's voltage and you grab whatever's live and you complete that circuit, or you close a loop to a different loop, an alternate path. The amount of current flow that's going to happen or run through you is going to be dependent on the resistance of your body. And let's say you get shocked by 120 volts. And let's say, for the math, I'll keep it simple since I don't have a calculator in front of me. Let's say your body is 1200 ohms. So on your calculator, I equals E over R. Intensity of current equals 120 divided by 1200. So you're going to have 0.1 amps flowing through you in that situation. And it doesn't sound like much, especially compared to the 48,000 that I was just talking about, but that's enough to kill you. And depending on your situation, there's so many variables involved in what I just said. Some people might just receive a shock. Some people might go into ventricular fibrillation. And there's a lot of other things that can happen in that situation. But just know that Ohm's law applies there. And the amount of flow that's happening through your body is proportional or inversely proportional to the resistance of your body. That's why GFCIs, ground fault circuit interrupters, are rated to trip at 0.006 amps. 6 milliamps or more, and in that situation, if that was protected by a GFCI, you wouldn't receive a shock. It would trip before you even felt that. There's a term that it's been used by a lot of people over the years, is that electricity flows the least path of resistance. That's kind of true and it's kind of not true, and I want to give you an expanded, correct way to say that, is that electrical currents will flow through all closed, energized, available paths to it. And the amount of current flow will be inversely proportional to the resistance of that path. So that's it for today. Next time, I'm going to talk about the foundation of alternating current with names and terms, and that one too. I'm going to talk about Michael Faraday, I'm going to talk about Nikola Tesla, and I'm going to talk about Thomas Edison. And hopefully the weather cooperates with me and I can go to another beautiful place to do my lesson from. I'm so glad that you're here watching this. I get excited about teaching you, and I hope that this has been helpful for you. Until next time, bye from the Yorkshire Dales and the Crimple Valley Viaduct.